Welcome back to this lecture on combinatorics. In this segment, we're going to discuss the concept of a permutation and the process for counting permutations. So let's say you start with a set of n distinct objects. Of course, the elements, the objects have to be distinct because a set cannot contain duplicates. Then we define the concept of a permutation of this set as an ordered arrangement of the objects in the set. So a permutation of a set is just a listing of all the elements in a set in some order. Now, of course, there are many ways you could list the elements of a set. There are many orders you could do it in. And counting this number is called counting the number of permutations of the set. So here is a theorem that gives you the formula. It says that given a set of n distinct objects, there are exactly n factorial permutations of these objects in the set. So to illustrate this theorem, let's look at an example. Let's consider the set with 3 elements, so n is equal to 3. The elements are A, B, and C. How many ways are there to list all of the elements of S in any order? Well, that list is going to look like a sequence of 3 elements. And now we're going to determine the identity of each element at each position in that arrangement. So how many choices do we have for an element to be put in the first position? Well, the answer is 3. Once you have picked an element for the first position in the arrangement, you have 2 elements left to choose from to put in the second position. And here we're going to use the product rule. So the total number of arrangements so far is 3 times 2. And of course, for the last position in the arrangement, we only have 1 choice left, so we just multiply by 1. And notice, this total number of permutations of the elements of set S is equal to 3 times 2 times 1, which is 3 factorial. So even though this is just an example, you could see how we could formally prove this theorem and obtain the n factorial number. Now, since 3 factorial is a small number, namely 6, we can go ahead and list all of the arrangements or permutations of the elements of S. First, we have the permutations that start with the element A. We have 2 of those, namely ABC and ACB. Then we have all the permutations that start with the element B, namely BAC and BCA. And finally, we have all the permutations that start with the element C, namely CAB and CBA, for a total of 6 or 3 factorial permutations of the elements of S. Now, a related concept is the concept of an r-permutation. So again, you start with a set of n distinct objects, and you build an r-permutation of that set by first picking any r elements in that set and then ordering them in a particular way, where r is a number, an integer that's smaller than or equal to n. So the number of these r permutations is denoted by PNR. So PNR is the number of permutations of r elements chosen among the n elements of a set S. So let's consider a theorem that would tell us exactly the value of PNR. So let's assume that we have a set of n distinct objects and that we have an integer r that is less than or equal to n. The question is, what is PNR? In other words, how many permutations of r elements chosen among a set of n elements are there? And the theorem states that PNR is equal to n, because you have n choices for the first element in the arrangement. And then you have n minus 1 choices for the next position. So you multiply the 2. Then you have n minus 2 choices for the next position, etc., etc. Now in this case, we're not going down all the way to 1 because we're only arranging r elements out of n elements, where r is potentially less than n. So when are we going to stop? Well, if you do the math, you notice that the last term in the product here is going to be equal to n minus r plus 1. Notice this looks like the factorial function applied to n. This is almost n factorial. So we can start writing it this way, except we're missing the terms that go from n minus r down to 1. And this product, of course, is equal to n minus r factorial. So to eliminate these terms from the product, we need to divide n factorial by n minus r factorial. And theorem 4 then gives us the number of permutations, p and r, of r elements chosen among a set of n elements. So remember that to build an r permutation of a set of n elements, you must first pick a subset of size r out of the set of n elements. Now there are many ways to do that in general, and for each way of picking a subset of size r, you must compute the total number of arrangements of these r elements. So what this formula tells you is instead of doing this computation and then adding up all of these numbers for all of the possible subsets, you can get the answer in one step. So let's look at a particular case of this computation where n is equal to r. So what does that mean? Let's do it intuitively first. How many subsets of size n are there for a set of size n? Well, the answer is 1. There's only one subset. That's the whole set. So we have one set of size r, or n in this case. And how many permutations do we have of these n elements? Well, the answer is n factorial. So the total number of r permutations of a set n when r is equal to n, that is p and n, is equal to n factorial. That's the intuition. So let's plug in those numbers in the formula and make sure that we get the right answer. If r is equal to n, then n minus r factorial is just 0 factorial, which is 1, so the denominator goes away and the answer is n factorial. So clearly the theorem works in that special case, which is a good thing. Now instead of proving the theorem, let's illustrate it with an example. Now let's say you were asked to cast a ballot for 3 different people, namely the best teacher at UWO, the worst teacher at UWO, and the hardest teacher at UWO. So you have to pick among all 800 teachers, and you would have to pick 3 different people. Apparently, the hotness of the instructor is a crucial factor in your learning experience. So the question is, how many different ballots would you have to choose from if you had to pick a ballot with 3 names on it, given that you would have to choose the 3 names out of a set of 800 teachers? So out of a set of 800 elements, you have to pick 3 elements or 3 teachers. And notice the order of the teachers on the ballot matters because, by assumption, the first position corresponds to your choice for the best teacher, the second position corresponds to the worst teacher, and the third one is the hottest teacher. So first you have to pick a set of 3 teachers, and then you have to order them, since the order determines, the category in which they win. So r is equal to 3 because you have to consider all the subsets of size 3, and then you have to count all of the arrangements. So according to theorem 4, the number of possible ballots is going to be equal to p and r. And in this case, we have p 800, 3. So if you use this formula here, this number is equal to 800 times 799 times 798. Of course, another way to write this is that it's 800 factorial divided by 797 factorial. And it turns out the answer here is approximately equal to 500 million different ballots. So make sure you're comfortable with the formula here in Theorem 4. So let's illustrate it again in the case of a concrete example. How many choices do you have for the teacher in the first position? Well, you have 800 choices. Now, for each one of these choices, how many choices do you have for the second position? Well, you have 800 minus 1 choices. And after you've made the first 2 choices, you only have 800 minus 2 choices for the third position. So using the product rule, the total number of ballots is going to be 800 times 799 times 798. Now, let me give you a practice problem for you to work on at home. I want you to count the total number of binary strings of length 10 that contain exactly 3 ones in them. Again, the total number of binary strings of length 10 with exactly 3 ones in those strings. How many of those strings are there? Make sure you work hard on this problem and you try to model it as a counting problem where you're counting a number of r-permutations, and therefore you can directly use this formula to solve it.